Hello friends, welcome to Ansys-Tutor. In this tutorial, we are going to analyze a heat transfer from a dimple surface. There is a pipe with wavy protrusions. It is a 2D symmetric geometry. Water is flowing through this pipe. The pipe wall and the wavy protrusions are at a temperature of 310 Kelvin. Find out the heat transfer coefficient and Nusselt number. The inlet velocity is 0.001 meter per second. And the protrusion's temperature is 310 Kelvin. We are going to find out the heat transfer coefficient and the Nusselt number. Open the ANSYS workbench. Drag the fluid flow fluent into the project schematic space. Select the geometry. Change the analysis type to 2D. Then right click on geometry and select new design modeler geometry. Now go to units and change it to millimeter. Select the XY plane. Click on the Z axis to make the sketch normal to the screen. Now click on the sketching toolbar. Draw a rectangle starting from this origin. Now put the dimensions to the rectangle. Click on generate. Go to the concept tab and select surface from sketches. Select the sketch, then click on apply. Select the operation as add frozen, then click on generate. A 2D surface, rectangular surface will be generated. Now create another sketch. Now go to sketching toolbar, then draw a circle. Now put the dimensions to the circle and this is the distance from this y axis. Now again go to create menu and select surface from sketches. Select the second sketch and generate the 2D surface. Select the operation as add frozen and click on generate. Now you can see the two surface body has been generated. Now go to create menu and select pattern option. Select the circular geometry as the geometry to be pattern. Select the direction as x axis. Enter the distance between these copies. Enter the number of copies. Then click on generate. Now we are going to boolean this pattern from this rectangle. Just select the boolean tool. Select the operation as subtract. Select the target body as the rectangle and the tool bodies as the pattern circular pattern surfaces. Then click on apply. Preserve tool bodies as no. Click on generate. This OB surfaces should be generated now. This is our geometry. Geometry is complete. Now close the design modeler and go to meshing to do the analysis. Now close the design modeler and open the meshing workbench. Right click on the mesh. Change the element size. Now go to sizing. Choose adaptive sizing option. Increase this resolution. And then right click on the mesh and click on generate mesh. The mesh cells are little bit larger, so we are going further decrease this mesh cell. So you need to decrease this element size up to further 0.010. Click on the mesh and generate the mesh. The mesh is generated. We can also further decrease this meshing, decrease it to 0.05. Cells are also distributed properly. Now insert an inflation layer around the surface surfaces so that there will be a better distribution of cells around these wavy surfaces. Select all this wavy surface, half circle. Select these as boundary. Then click on apply. Enter the inflation option as total thickness. Enter the number of layers, maximum thickness up to 0.1. Right click on the mesh and click on generate mesh. The inflation layer has been created. It's little bit smaller cells has been distributed around these wavy surfaces. We are further decreasing this. Now we are going to add named selection. Enter the inlet and outlet. Select the inlet surface, name it as inlet. Select the outlet surface and name it as outlet. Select the bottom of the rectangle and name it as axis. Now we are going to select all these OB surfaces. And name all these surfaces as adjacent heat flux boundary. Turn up the mesh. Let's see, check all these named selection has been assigned properly or not. Go to mesh and select update mesh. The mesh will be now be linked with the Fluent solver. Now close the meshing and open the Fluent solver setup. Right click on the setup and click on edit. Select the double precision model and click on start. Select the 2D space as axisymmetric. Go to models. Turn on the energy equation. Select the viscous model. Select the laminar flow model. Now we are going to add the materials. Double click on fluid. Go to the Fluent database. Select water liquid as this material. Click on copy. Then click on change, create and close. Now go to cell zone conditions. Change the default material from fluid to water liquid. Now we are going to assign the boundary conditions. Filter the boundary condition as per these types. Select the inlet. Click on edit. Enter the velocity magnitude as 0.001 meter per second. Keep the normal or atmospheric temperature input. Then click on OK. Now the outlet, keep the default pressure outlet boundary condition. Select the walls. Then click on edit. Enter the temperature boundary condition to this cylinder hot walls. Then click on OK. And this keep pipe wall as adiabatic walls with heat flux 0. Click on OK. Now go to methods. Change this spatial discretization gradient as green Gauss cell based discretization. Now go to monitors, select residuals. Decrease the energy residuals up to 10 to the power minus 30. Now go to initialization. Select hybrid initialization and click on initialize. Hybrid initialization is done. Now go to run calculation page. Enter the number of iterations as 1000. Then click on calculate. It would take some time to do the iterations. Now the calculation is complete. Go to the results section. Select reports. Click on the surface integral. Select the report type as vertex average. Enter the field variables. Field variables as wall fluxes and surface heat transfer coefficient. Now select the hot cylinder wall surface. To get the heat transfer coefficient on the surface. It is found that heat transfer coefficient is 11.077 watt per meter square Kelvin. Using this heat transfer coefficient, we are going to find out Nusselt number. Now close this Fluent server setup and open the results section to see the variations in these results. Open the results. Insert a new contour. Select the domain as all domain. Select the location as the periodic 1 walls. Then click on OK. Select the variable as temperature. Select the global range and number of contours as 100. Then click on apply. This is the variation of temperature around these wavy surfaces starting from inlet to outlet. We are going to modify this different legend view. Change it to as fixed value and click on apply. Similarly, we are going to find out the velocity contour also. This is the temperature contour. Temperature is highest at the wavy surfaces. Now save this image, contour image. Now we are going to find out the velocity contour on this surface. Select again this contour. Change the variable as velocity. Then click on apply. This is the variation of the velocity around this contour. Similarly, save this velocity contour image also. Now we are going to add a streamline to see these flow variations along this wavy surfaces. Select start from inlet, enter the number of points as 100, then click on apply. Now we are going to animate this flow. Select the quick animation, select the streamline, click on the play button to observe the variation of the flow along this wavy surface. The flow velocity can be seen that it is maximum at this axis of this domain and it is decreasing towards the boundary surface. Now we are going to observe the full domain using this reflection of the contour image. Select the contour, go to the view tab, click on apply reflection or mirroring. Select the plane around which you want the reflection, then click on apply. The contour would be reflected. Now create another contour which would be at the original position. Select the variable, enter the number of contours same as this previous one, then click on apply. Turn off the wireframe. Now this is the full domain body view. Now save this image. Similarly, save the temperature contour also. Now insert a velocity vector. Insert a velocity vector to observe the velocity variations around these wavy surfaces. Similarly, find out the velocity vector around the entire body. With this, let's conclude this demonstration. Hope you would like this tutorial. If you have any suggestions or query, please feel free to ask us. Like, share and subscribe to Ansys-Tutor. Keep learning and keep exploring. Thank you.